Okay guys, so the next topic we are going to study is amine inversion. So what is known as amine inversion is simply we have a nitrogen atom at room temperature which is substituted with three other atoms. It may be, just in this case, the isotopes of hydrogen. So this nitrogen atom also has a lone pair, making its hybridization as sp3. So what will happen is this sp3 hybridized nitrogen atom undergoes inversion at room temperature to convert itself into inverted compound, just like this. So how does this inversion happens? So the inversion requires some activation energy which is available at the room temperature, and the transition happens wherein the lone pair of nitrogen atoms goes from s orbital to p orbital. Hence this intermediate product is actually sp2 hybridized, wherein the lone pair reside in p orbital rather than in s orbital. Okay, and again when the transition or the inversion happens, the sp3 hybridization of nitrogen is regained. So the lone pair comes to the p orbital, making the hybridization of nitrogen as sp2 from sp3, and again after conversion or after inversion takes place, it again converts itself from sp2 to sp3, or in other words lone pair again comes back to the s orbital from p orbital. Okay, so the inversion actually takes place at room temperature. No invert okay, so I will take some of the examples in which no inversion will take place, and will tell you why the no inversion will take place. Because in this case no nitrogen is there. Amine inversion, the first, as the name suggests, the first criteria or the condition for amine inversion to happen is the compound must have a nitrogen atom in it. In the second case, why inversion will not take place is because this alkene group is a bulky group which will restrict the inversion of nitrogen at room temperature, because for the inversion to take place the inversion energy should be available at room temperature. So in this case you need to actually provide the activation energy or EA to the compound for inversion if you want to see the inversion in this compound. Similarly, in this compound nitrogen atom is sp2 hybridized, and the condition for inversion to take place is the nitrogen should be sp3 hybridized. Okay, so inversion actually decreases the basic strength, as by flipping the lone pair goes to the p orbital and again comes back to the s orbital. So the dancing of lone pair between s and p goes on, s and p orbital goes on. Hence the nitrogen did find its ability to contribute its lone pair to the acidic compounds decreases. Okay, so inversion does not take place in acidic medium because the plus charge of nitrogen will easily be donated to hydrogen. Inversion takes place in basic medium. I hope you understand the reason why. Okay, so next we are going to talk about SIR effect. In SIR effect, I just redraw the structure here, so for you guys to see more clearly what this structure is all about. So in this structure we have a phenyl ring substituted with two methyl groups, and we have a carbocation attached to the phenyl ring, and it is also having two CH3 groups attached to itself. So now what happens is these two phenyl groups, as they are more bulky, will actually have steric repulsion between each other, and this will cause the compound to lose its planarity. So what do I mean by losing the planarity is to avoid or to reduce the steric hindrance between these two carbon atoms. The compound actually twists the bond between the phenyl ring and the carbon atom so as to accommodate more space for each of the phenyl groups in each of the carbocation as well as the phenyl ring. So suppose the phenyl ring is in one plane and the carbocation actually rotates itself and the other two CH3 groups along with itself into a perpendicular or near perpendicular plane to the phenyl ring. So hence what is the significance of this rotation? If the rotation occurs on this bond, then there will be no conjugation between the pi bond we can find in the phenyl ring and the carbocation. And if there is no conjugation, hence there is no resonance between the carbocation and the phenyl ring. So the phenyl ring and the carbocation loses their capability to have resonance with each other. Hence this compound will have more resonance with when compared to this compound. So the restriction of resonance due to steric hindrance is known as SIR effect, or steric inhibition of resonance effect. Okay, we will take one more example so as to make you understand what we are talking about. So let's say we have this compound in which we have nitrogen which has one lone pair and two groups attached to itself, and the same groups are attached to phenyl ring. So SIR effect takes place in this compound as well. Why? Because these two methyl are having steric hindrance with each other, so as to reduce the steric hindrance, this nitrogen and the carbon bond will rotate itself and will be in two different planes, just like in these cases. This will be in different plane, and nitrogen with two methyl groups attached to each other will be in a perpendicular or near perpendicular plane to methyl ring with two CH3 groups. So as a result of this, no resonance will take place, and the lone pair will remain intact with the nitrogen atom only. So as the lone pair are intact with the nitrogen atom has more ability or capability to donate its lone pair to a needy group or a acidic group. Hence its basic strength would be more than the phenyl ring with nitrogen atom attached with two with the two CH3 groups. And why? Because in this thing you can see that the nitrogen atom will have a lone pair, and the lone pair will be involved in resonance with the phenyl ring. Okay, so the rotation of nitrogen and phenyl bond, because of the rotation of the sigma bond, there will be no resonance because of the SIR effect. Okay, so let us compare the basic strength between these two compounds, right? So as you can see that in this compound we have NO2 group attached, but in place of CH3 here we have HH, simple HH. So what will happen is, in this compound there we can see the SIR effect as we just explained in the above example. So there will be no resonance between the lone pair on this nitrogen atom and in the phenyl ring. But in this case what will happen is, this hydrogen attached to the nitrogen atom and this oxygen atom attached to this nitrogen atom will have a intermolecular hydrogen bond. We'll delve into what is called hydrogen bond into the future lectures, or you may find it in my inorganic lecture series. So due to the presence of this intermolecular hydrogen bond, the rotation is restricted across this pi bond, across this sigma bond, and as a result of that, this lone pair will get into resonance with this phenyl ring. Okay, so there will be no SIR effect in it. So due to the intramolecular hydrogen bonding, compounds get planarity and the lone pair gets involved in resonance with the phenyl ring, hence decreasing its basic strength, and thereby increasing the basic strength of this is already increased by SIR effect. Okay, so let us take one more example of SIR effect, wherein we need to compare the bond lengths of A, B and C bond. So C bond is between sulfur and this carbon atom, A bond is between sulfur and this carbon atom, and B bond is between sulfur and this carbon atom. So what would be the order of bond lengths of the following bonds? So as you can see, there it is a bulky group between I and SO3, so there will be an steric SIR effect between, so the compound will lose its planarity, but on the other hand we have a pi bond and electron negative element at the carbon position, so it will involve in its resonance, so that will have this bond will have a pi bond character. Hence the length of, as I have mentioned earlier also, that the length of pi bond is smaller than the length of sigma bond, hence B and C will have equal length and they both will be greater than A. So some of you might have questioned that what should be, or where, or what nature of groups should be at the or at the two ortho positions of NMe2 or this structure, so that we can actually have a fair look whether SIR effect is going to happen or not in this compound. So this G1 or G2 may be any combination of either methyl, nitro, iodo, bromo or sulfur group. So with this we end this lecture, and in the next lecture we will be seeing more such examples. With this, good luck and goodbye.